Good morning, everybody. Hope you can hear me. So nice that you're here in the breakfast sessions, although it's very early in the morning. So we have two talks today. The first one is Synthesis by Hila Peleg. Hope I said the name right. So,
thank you. Good morning. So I decided that I'm not going to really talk about the actual papers in the session, because the author is going to do a much better job at that than I am. So what I'm going to do is tell you about what program synthesis is and how I think you should listen to a program synthesis talk. So if you know stuff about synthesis, Victor, then you're going to be awfully bored. So I should probably start by telling you what synthesis actually is. And a synthesizer is a magic box, as we have many of those in PL. And it's a magic box that takes in some way to express what you would like code to do, and hopefully outputs that code, or some code that is that. But we're at POPL, so we don't like diagrams like this. We like diagrams that look a little more like this. So what is program synthesis? Program synthesis is the problem in which we would like to find a program from some language of programs defined by, a domain, a DSL, a something, where for every input that we can give that program, it is going to behave correctly on that input. And there's two main questions that you're probably taking away from this explanation that are basically what constitutes the majority of synthesis research. The first is, how do you find a program? That seems hard. And the second is actually, how do you tell it what is correct? And I'm going to start with the second one. Because it's A, easier to explain, and B, leads nicely into the first one. So how do we express what is a correct program to a little magic box? There's loads and loads of ways. This is not even a comprehensive list. I tried to touch on the ones that are relevant to the session. A very common one is examples. So I would have a set of input-output examples. When given this input, my program will produce this output, or this effect, or this exception, or something like that. We can also do types. Can be normal types, can be fancy types, but given stuff of these types, produce something of that type, also super popular. We can do a reference implementation. Please give me a program that behaves like this program, but under more constraints or less constraints, or in a different language, or something like that. We can do logical specifications. They're usually not going to be full logical specifications, because no one has time for that. We are lazy users after all. But it's going to be things like asserts in the code that we would like the result to adhere to. And then one thing that I'm going to expand on just a tad, because it's super relevant and also kind of unlike all the others, is called sketching. And sketching is basically a way to say, I kind of know what some of the code in this program should be. I just don't know all of it yet. So I would say something like, this is a sketch that I borrowed from Smith's demo page because it was a really convenient place to grab it from. And I'm going to say that there's something that I don't know and I would like the synthesizer to fill in that goes here. And I'm not going to explain to the synthesizer specifically what this little hole, we call this the hole in the sketch, should do. What I'm going to do is I'm going to tell it what the full program should do. The full program, the full insert function, should behave like this. And it's now the synthesizer's role to take that and turn it into a specification for that. And if it can do that, party time. Now, it may makes sense to you already, but if it doesn't, I'll just say it. Sketches never come alone, right? A program with a chunk that should do something is not a useful way to express correctness. It's always going to come hand in hand with like an assertion around the whole in the sketch, or examples either for the sketch itself or for the full thing, or maybe we at least know the type that should go in there, so we're going to guess by type. Sketches are always going to go with hand in hand with something else. Okay, so we've started making our way towards how are we actually going to find a program. I would like to find a program that does a thing to return to my user or put in my hole in the sketch. And as it may or may not surprise a person attending POPL', that is a hard problem. It's actually also super not surprisingly an undecidable problem. Immediately breaks the rice theorem. We love that. And the more you try to do in synthesis, the harder it becomes. So, that's just great. So what do? As always, we reduce the scope. We try to solve an easier problem. So the immediate easier problem that we can try to solve is, well, I would like to generate a program that behaves the way I would like from a very restricted target language, and let's say up to a predetermined size, or that I can spend no more than 40 seconds looking for, or something that makes this, hard, but at least will terminate. And now that I've at least said, okay, here, I now have a small, finite even, space of programs that I would like to look for a program in, I still need to look for a program. So how do I do that? And I'm going to be super radical here. People are going to get angry at me, but I'm going to make the claim that like 99% of synthesis follows one specific formula, which is generate a random program in the space, try it against the specification, see if it's any good. Practically all synthesizers do some flavor of this. Of course, the reason is that it's super high level, and I didn't give you any useful information as to how this is done. So in column 1, we have a bunch of options as to how we can generate programs. For instance, we can methodically enumerate the space and build all of the term trees that are available to us in there. And we can do it top down, so from a root node expanding downwards with productions, or we can do it bottom up, so making smaller programs and then composing them into larger programs. We can build representations of the space of programs, automata, graphs, other data structures, and then try to traverse them and find a solution. We can take deduction rules and proof rules and try to find a proof that matches our specification, and hopefully a program follows from the proof tree. We can do all of these things. You may notice, by the way, that practically all of these things are exponential, at least exponential searches of the space. It is unfortunate, still the best we can do. In column B, we get to do, for the most part, slightly easier work. For instance, we can run tests. If we were given unit tests or examples or whatnot, we can run them and see if it matches. Or we can take whatever it is that we got in the first column and encode it for an SMT solver, give it to the solver and see if it works. That's the non-easy option. We get to pretend that SMT solvers don't do like a lot of hard work, but they do. They're cool. Or we can, do simple things like type the expression and see that it types, which, depending on how fancy your types is really easy or really hard. But yeah, we're still going to have a problem at this point, because at this point we're still doing really hard work, and then moderately hard work to check. And if we have a finite but very large space, then at the worst case, we're going to do this for every single program. So what do? Well, obviously we cheat. The question is how. And the way that we cheat is that we fold the information that we know about our specification back into how we do the search. Now, every synthesizer is going to do this a little differently, but what we're going to do is that we're not going to just blindly generate a random program in the random space of programs. We are going to only look at programs that we can tell from the start are relevant to the specification that we're trying to synthesize for. And if we've done that, we're still going to work exponentially hard, but we've reduced some of the constants in our exponent, so maybe we're going to do a little bit better. Okay, so what can we do with program synthesis? We can take the code that comes out and we can put it in the IDE. That's not going to happen in this session, but that's a thing that you can technically do. We can use it to fix bugs. We know where a bug is, so we're going to make that code go away. Now we have a hole in a sketch. We're going to synthesize new code. We can take a reference program and try to synthesize a better one for some definition of better. Some of those are going to be around in this session, so keep your eye out for them. So to conclude, I kind of want to give you a recipe for like how to listen to a synthesis talk or how to read a synthesis paper should you ever choose to do that. First, you ask yourself, what is the goal? What are they trying to synthesize? Why are they trying to synthesize it? What problem are they actually solving? Is this going to a person? Is this going in the IDE? Is this to optimize code? What's the domain of programs? So what's the limited space that they've chosen to work in? What are the specifications? How is correctness being specified to the little magic box? How is the search being done? And most importantly, how are the specifications and domain being folded back into the search to help it along? I hope this helps you enjoy the synthesis session. Come do synthesis work, it's cool.